welcome back. Now we're going to cover the theory of beat frequency. The definition of beat frequency is the combination of two waves that have slightly different frequencies at a certain position in space, right? So we can set here, I have the equation y1 x of t is a sine k1x minus omega 1t. This is a equation for a traveling wave, y2 x of t, a sine k2x minus omega 2t. So we can set x equal to 0, just to make things simple. Set x equals to 0 and analyze what happens to these waves as a function of time when they combine together, right? So to make our life easy, we can just set x equals 0, this thing disappears, and I have y1 0 of t is equal to a sine of negative omega 1t, which is equal to negative a sine of omega 1t. But I can just take its absolute value since I'm just interested in the combination of these waves, and it doesn't matter if I take it as a negative or just its absolute value. So right now, just take the absolute value of that, right? And then I'm going to have y2 0t is going to be a sine of negative omega 2t, which is going to be a sine of omega 2t. And then again, take the absolute value of that. So now, analyze what happens to these waves as a function of time when they combine together, when they have slightly different frequencies, right? So y total, right? And then we're going to apply that trig identity to this. We have y total 0t is equal to 2a cosine of, and then my a is going to be one of these, right? Either omega 2 or this one. So we're going to say omega 2 minus omega 1 over 2t, right? Times sine of omega 2 plus omega 1 divided by 2t. And then we're going to analyze what this equation will look like, what its behavior will be, right? Going to go something like this. Then it's going to go back down, then it's going to go back up, then it's going to go back down, and so on. And then there's a bigger envelope here. You see a bigger pattern. Okay, so since this one, omega 2 minus omega 1, is a smaller frequency, that determines the bigger envelope, right? In other words, this occurs less often and determines the bigger pattern. And then this one is omega 2 plus omega 1 is a bigger frequency. It's the inside pattern. In other words, it's occurring more often, right? And if you take the ratio of the frequencies, omega 2 plus omega 1 divided by omega 2 minus omega 1, that tells you how many more times the inside pattern is occurring than the outside bigger pattern, right? So this is the ratio of the inside pattern to the divided by the outside pattern. Okay? So this outside pattern is what is known as beat frequency. Beat frequency. In other words, the beat frequency is a measure of how often the outside pattern occurs, how many cycles per second the outside pattern occurs, right? So if you have two sound waves, F2 is equal to 2 cycles per second, and F1 is equal to 1 cycle per second, we would like to know if these two waves interfere with each other, what will the beat frequency is. And it's going to turn out that the answer is the difference of the two. So let's calculate how we can come up with the beat frequency, right? So let's assume that this point is some point in time t1, and then this point is some point in time t2. What requirement will that satisfy, right? So we have, in the equation, we had cosine of omega 2 minus omega 1 over 2t, right? So the beginning of the bigger pattern, you see here, the bigger pattern is beginning. This omega 2 minus omega 1 over 2t must satisfy what? Well, it must satisfy pi over 2 plus n pi. Because cosine of pi over 2 is 0, and any n pi multiple of it is also 0, right? If this satisfies this condition, then cosine will be 0, right? So then let's say this one, the first one occurs when n is equal to, this is a, so this first one can occur when n is equal to 0, right? And then when n is 0, this one will be just pi over 2. So that will give us t1. t1 is equal to pi over 2, right? And then we can, from there, we can solve for t1. What I would like to express is the relationship between omega and the frequency, right? Remember, omega was equal to 2 pi times the frequency, so then I can substitute that there. I can say 2 pi f2 minus f1 over 2 t1 is pi over 2, right? And then the pi will cancel the pi, and then the 2 will cancel the 2, and then what will I get? t1 is going to equal 1 over 2 f2 minus f1. So depending on what the difference of the two frequencies are, 2 minus, if it was 2 cycles per second, right? And this is 2 cycles per second, then it would be 2 minus 1, it would be 1, and then t1 would equal 1/2 second. So there would be half a second right here is when the first beat would begin, right? So now what would t2 be right here, t2? Okay, so for t2, n would be 1, right? That's the next time when cosine is 0, right? So we just put omega 2 minus omega 1 over 2 t is equal to, if you put n is 1, you get 3 pi over 2. And again, we're going to use the fact that omega is 2 pi f. So we can say 2 pi f2 minus f1 over 2 t2, right? 3 pi over 2. So this one we're calling t2, so I'll put the subscript t2. And then the 2 cancels the 2, pi cancels the pi. Then we can solve for t2. t2 is equal to 3 over 2 f2 minus f1, right? So again, if the f2 was 2 cycles per second, and if f1 was 1 cycle per second, this one would be 3 over 2, so it would be 1.5 seconds. 1.5 seconds, right, in that case. So then what would the difference of those two times be? T2 minus T1. Well, that would be the period of a beat, right? In other words, how many seconds it takes for a beat to start and then the next beat to begin, right? So that's going to be the period, and then the frequency of the beat is going to be the reciprocal of that, right? So T2 minus T1 is the period of the beat. Okay, so then we can say 3 over 2 f2 minus f1 minus 1 over 2 f2 minus f1, right? In other words, it's just, you just subtract this and you just get 1 second, right? The period will be 1.5 minus 1/2, 1 second. And then the beat frequency is the reciprocal of the period of the beat, right? So then it's just going to be f beat is going to be 1 over t beat. It's going to be f2 minus f1. So in this case, if the period is 1 second, the f beat is going to be 1 over 1. So it's just going to be 1 beats per second, right? And you will hear one of these beats every second, right? Well, how many small envelopes will there be in that case? How many small envelopes inside of the beat envelope, right? So remember, we had omega 2 plus omega 1 over omega 2 minus omega 1, which is the same as f2 plus f1 over f2 minus f1. So it'll be 2 plus 1 over 2 minus 1. It'll be 3 over 1, which is 3. So the picture will look something like up, and then back down, and then back up, and back down, and then back up. So you see up, down, and then back to the start. So you see that'll be a ratio of 3 to 1 small pattern within one beat frequency pattern, right? What if f2 was 4 hertz and if f1 was 2 hertz? What would the beat frequency be? F beat would be 2 hertz. It'll be their difference, and then the ratio will be 4 plus 2 over 4 minus 2, 6 over 2, which is 3. So the ratio will be again 3, right? So the only difference is that now, what would T1 be in our case? T1 would be 1 over 2, and then F2 minus F1 will be 4 minus 2. So 1 over 2 times 2, 0.25 seconds. So the first time over here would be 0.25 seconds when the beat frequency begins, right? And then T2 is going to be, same equation here, 3 over 2. So 3 over 2 times 2, 3/4, which is 0.75 seconds. So what happened? The envelope is now smaller because the beat frequency is faster, right? So now it's going like this, 0.25 and then 0.75, so it's going up and down really quickly. So the period is going to be 0.75 minus 0.25, which is 0.5 seconds. And then this is the period of the beat, and then the frequency of the beat is going to be 1 over half, which is 2 hertz, which is exactly what we got here by subtracting them, right? So then, how many of the small patterns will there be within the larger pattern? Again, it will be 3: up, down, and then back up, right? And then continues to go that way, up, down, and back up, like that. And then you can do any kind of combination like that. You can do 4 and 3 combination, right? And then what will that be? The beat frequency will be 1 hertz. The ratio will be 4 plus 3 over 1, 7. This is going to be 4 minus 3, so it's going to be 0.5 seconds, right? So in that sense, it's similar to the previous one, where it started at 0.5, and then you got the bigger envelope, like this. Right? And then this one is going to be 3 over 2, 1. So it's going to be 3 over 2, it's going to be 1.5 seconds. So this is 1.5 seconds. The period of the beat is going to be 1 second again, and then the frequency is going to be 1 over 1, which is going to be just 1 hertz, right? The only difference is now there's a lot of the smaller patterns within the larger pattern, right? So then how many of those are there? 7. So up, down, 1, 2, 3, 4, 5, 6. I'll continue like this. 1, 2, 3, 4, 5, 6, 7, and then it'll continue like that. But the beat frequency will still be 1 cycles per second. So now you can see how this phenomena plays a role. Beat frequency plays a role for sound waves that interfere with each other. They make beats, and also other waves that interact with each other. It could be waves in strings. They could also make this kind of beat frequency phenomenon, okay? So now you see how this works. Thank you very much.